Have you ever stopped to wonder how your phone just knows it's your face? Or how a self-driving car can navigate a super busy street? Well, today we're going to pull back the curtain on the magic behind it all. We're talking about convolutional neural networks, the powerful engines that are, for the first time, really allowing machines to see. Okay, take a look at this picture. When you see it, your brain does something absolutely extraordinary. In a split second, it pulls together shapes, textures, and memories and tells you, yep, that's a cat. Simple. But what does a computer, a machine that's just pure logic and electricity, see in this exact same image? You see, to a computer, this isn't a soft, furry animal. It has zero concept of cute or cuddly. What it actually sees is just a grid of numbers, a massive spreadsheet of pixel data. So the real question, the one we're going to unpack, is how does it get from that cold, hard data to a simple, confident label, cat? To crack that code, we've got to start right at the beginning, with how a computer even perceives an image in the first place. So forget about pictures for a second. For a machine, it's all about the numbers. Every single image you've ever seen on a screen is, at its core, just a giant grid of tiny dots called pixels. And each one of those pixels is represented by just 3 numbers, basically how much red, green, and blue light is in it. So this whole complex, detailed image of a cat, it just boils down to a massive, sprawling array of numbers. That's it. That is the only thing the machine has to work with. All right, so you've got this huge grid of numbers. What's the most obvious way to get a computer to recognize what it is? Well, it turns out the most obvious answer was also a really, really flawed one, and it led to a huge problem that stumped researchers for a long time. Early attempts did exactly what you might think. They just took that 2-dimensional grid of pixels and completely flattened it out, kind of like stretching a t-shirt until it's just one long thread. They created one incredibly long list of numbers to feed into a standard classifier. But in doing that, they accidentally destroyed the single most important piece of the puzzle. Think about how you knew it was a cat. You didn't just see a random collection of eye pixels and ear pixels. No. You saw that the eyes are below the ears and on either side of the nose. It's this spatial relationship, where things are in relation to each other, that's absolutely everything for recognition. And when you stretch that image into one long list, you completely sever those crucial connections. A pixel that was once right next to another is now thousands of spots away in the data line. The network loses all sense of space and proximity, which makes it almost impossible to learn any meaningful patterns. And this really sums it up perfectly. The core challenge was that these early methods just didn't respect the fundamental structure of an image. They treated it like a jumbled up bag of numbers, not a structured, meaningful grid where location matters. So how do we fix this? Well, we need a totally new kind of neural network layer, one designed from the ground up to understand that spatial structure. And this is where the hero of our story comes in, the convolutional layer. So instead of flattening the image and losing all that precious information, a convolutional layer works directly on the pixel grid itself. It uses these small windows called filters that slide over the image looking for specific patterns, and it preserves the where of everything it finds. A really great way to think about this is to imagine each filter as a tiny little detective, and each one has a very specific assignment. One detective might be on the lookout for vertical lines. Another might be tasked with finding patches of green. Maybe a third is searching for a very particular curve. They're all specialists, each with a single job. So here's how it actually works. The little featured detective, our filter, slides over every single possible spot on the image. At each stop, it looks at the small patch of pixels right underneath it and calculates a score for how well that patch matches the feature it's looking for. All of those scores are then put into a new grid, which we call an activation map. And this map is basically a cheat sheet, highlighting exactly where in the image our detective found its clues. Okay, so we have these detectives that can find simple little clues like edges and colors, but that's still a really long way from recognizing a whole cat. The real magic, the part that's truly brilliant, happens when you start stacking these layers on top of each other. So the very first layer works on the raw pixels, finding those simple features. But the second layer, it doesn't even look at the pixels. It looks at the activation maps from the first layer. So its detectives are looking for patterns in the patterns. They learn to combine edges to find corners, or blend colors and textures. And as we go deeper into the network, the detectives just get more and more sophisticated, combining corners to find eyes, combining eyes and noses to find faces, building up this amazing hierarchy of knowledge.
And this right here, this is the real aha moment. On the left, you can see what a simple, non-convolutional network tries to learn. It's just these blurry, whole image templates. It's trying to memorize an average car. But now, look at the right. This is what the first layer of a convolutional network learns. It's not learning cats or cars at all. It's learning a whole library of reusable building blocks, lines, color gradients, little patterns. These are the fundamental pieces it can then use to build any object. It's just a more powerful and efficient way of learning.
Now, there's one more key piece that works with convolution to make these networks even more effective, and this helps us build our final complete picture. And this is called a pooling layer. So, after a convolutional layer makes that really detailed map showing exactly where a feature was found, the pooling layer comes in to, well, summarize it. It basically just shrinks the map down, keeping only the most important bit of information, like the highest match score in any given neighborhood. So why would you do this? Well, there are two big reasons. First, it drastically cuts down on the amount of data, which makes the whole network faster and way more efficient to train. And second, by summarizing, it makes the network less sensitive to the exact location of a feature. It doesn't really care if an eye is a few pixels to the left or right, which makes the whole recognition process much more robust and flexible.
And so here it is. This is the classic recipe for a convolutional neural network. You just repeat this block of operations. You use a convolutional layer to find features, then a pooling layer to summarize them. After you do this a few times to build up that deep hierarchy of knowledge, you finally flatten the result and use a standard classifier at the very end to make the final call. Is it a cat, a dog, or an airplane? So now that we've seen the whole architecture, let's circle all the way back to our original question. After all this incredible, complex processing, what has the computer actually learned? What does it truly see? Well, the answer is both fascinating and, honestly, a little bit weird. What you're looking at are visualizations of the final templates the network has learned for each category. They're not crisp, clean pictures, are they? They're these abstract, almost ghostly patterns that represent the most important features. To the machine, a car is this specific blend of shapes and colors. A cat is another. It's a totally alien way of seeing, based entirely on statistical patterns. And this all leads to a really fascinating final question. The machine can label an image as cat with incredible accuracy, right? It's learned the statistical patterns perfectly from its training data. But when you look at these abstract templates, does it really understand the concept of a cat with all the context and behavior and meaning that we associate with it? Or is it just an incredibly sophisticated pattern matching machine? And that's a question that pushes us beyond the code and right into the very definition of intelligence itself.